Oh, I see Nikola. Good morning.
Morning. How are you?
Fine, thanks. How are you?
I'm good.
Bit early, I guess.
Yeah,
Sorry,
that's a little early.
Hi, Hu.
Hi, Jimmy. Thank you so much for the invitation.
Oh, yeah. Welcome. Thanks for joining.
Thank you.
Nothing.
Probably it's a bit too late. So my student, I don't see my student. Some students should come.
Yeah, it's like what, 12:30?
12:30, yeah, now in the evening.
Yeah. Hey, hi, good to see you.
Yeah, Peng Chen, nice to see you. Yeah. Now the web is so convenient, huh?
Yeah, that's right.
Yeah, that's good. Yeah. This year, the Beijing Forum will be in Chongqing and in May. Will you come back?
Yeah. Well, yeah, I'm gonna try. I mean, yeah, I don't know. I had one vaccine. If I get 2 vaccines, I'll be able to travel with 1 vaccine.
Oh, I see. Okay.
So I'm taking one more shot early April.
Okay.
Good morning, Ian.
Good morning. How is everyone?
Hey, Ian. Good morning.
Good morning.
Yeah.
I see friendly face, Rick. Hi, Rick.
How you doing?
Oh, hi, Rick.
Well, good to see you.
Good to see you. How are you?
Long time no see.
Okay.
Hi, Rick.
Yeah.
Hello.
Hi, Peng Cheng. Yeah, I'm sitting in Florida.
Yeah.
Oh, you're warm.
Yeah, Ian will tell you. I'm working very hard.
Very hard. When are you coming back to Maryland?
I'm coming back in about 2 weeks.
Oh, okay. I was expecting you to say never. You were just going to.
Oh, no. I'm coming back in 2 weeks. Yeah.
So the temperature is that high? I found you were a little. Rick?
Oh, no, it's very nice in Florida. It's 70 degrees.
Florida.
Yeah, so I spent the whole winter here.
Oh, I see. Okay,
yeah,
good.
to get away from the COVID-19 and also the cold weather.
Yeah.
I guess you teach online, right? You can just remotely teaching, yeah.
Yeah, well, I'm not teaching this semester, so that made it easier. But last semester I had to do remote teaching. Yeah. It worked fine. It was very good because all this, it started out with 60 students, and I was so bad at Zoom that by the end of the semester there were only 5 left. So it was very easy.
Good for you,
Don't say that too loudly, Rick.
That's the secret of good Zoom teaching. No, I'm only kidding. Believe it or not, I got better ratings in my course teaching by Zoom than I did in person.
I see.
I mean, it's kind of weird, really weird, but it's, as you know, I don't find it as satisfying. It's not.
Yeah.
No. Yeah.
Well, you have to pay attention. That's for sure.
Yeah, that's true. Anyway, yeah, I will join you here for part of this seminar. I don't know.
I think we're still gathering. Hi,
oh, okay, good. Hello, hi, Hu. I didn't say hello to you.
Yeah, hello, Rick. Yeah,
good to see you
here. Yeah, good to see you. Yeah, Henry.
Oh, Henry, hello. Ah, yes, fantastic.
Trying.
How are you?
Well, doing as I can with COVID. But...
Yeah, I mean, Paris sounds very bad.
I don't know whether it's bad. It's less than in the US, no?
No, but some of us are getting vaccinated. I'm fully vaccinated.
Vaccination.
Me too.
I am too.
Oh,
not
okay.
fully. I got the first one. But, well, the children go to school here. There is a big difference with many other countries in Europe.
Yeah, that's true.
And this has been a political choice to get the schools running.
Yeah.
Places where they have stopped completely the schools, I don't know. This will lead to some problems.
Yes, well, that's been one of the problems in the United States, I'd say. a lot of, you know, people have really missed almost a year of school. This is very bad. Yeah.
Here, apparently, last year they lost a part, but this year the schools have opened in September and not fully on well, part of the high school cases were with Zoom or with at distance, but in many places they have been open fully. I know, but my grandchildren go to school. Totally.
Hi, you guys.
Hi, Hilbert. Hi, Nigel. Great to see everybody. I think we'll get started. We have a quorum. Nikola,
42 people. That's very good.
Sure.
Nikola, you want to start? Oh,
Yeah,
maybe are you a co-host?
Yeah.
Okay.
Let's see.
Good.
Okay, is this working?
Yeah, it's good. Looks good. Yeah.
Okay.
So welcome to everybody and thank you for joining in. We have two talks today concerning quantum criticality in the ionic-tides. And so we're delighted to have Nikola Maksimovic to start off. Nikola, the floor is yours.
Thanks. Thanks for the introduction, and thanks for inviting me to give this talk. So I will mainly be talking about the magnetoresistance of the phosphorus-doped Barium-122 series. I want to give a special shout out to my collaborators first. So I'm a graduate student in James Analytis's group, so special shout out to James. Vikram Nagarajan and Ian Hayes, the next speaker, were instrumental for the crystal growth and also data collection in this project. Alex Koshelev at Argonne did much of the theoretical modeling that I'm going to discuss. Thomas Schenkel and Yunbei Kim from Lawrence Berkeley Lab were involved in this disorder experiment that I'll discuss. And then John Singleton at the Mag Lab was basically there for all of the data collection in pulsed field. So let me give a brief outline of my talk first. I'll give a few slides of background of why it's at all important to measure magnetoresistance in high temperature superconductors or quantum critical metals. And then, you know, over the past few years, there's been a series of experimental studies that have kind of built up this phenomenology that I'll describe and what the open problems are. And the bulk of my talk will be focused on presenting an orbital magnetoresistance model for explaining several features of the data seen in Barium-122. In particular, the model is based on magnetoresistance in the presence of what I call quasi-particle sinks on the Fermi surface. These are either regions of very high Fermi surface curvature or very high scattering rate. And these are applicable to underdoped and optimally doped Barium-122 respectively. Finally, I'll have basically one slide of potential applications to other high temperature superconductors. So of course, here's the motivation for magnetoresistance measurements. I've plotted here the very famous phase diagram of the phosphorus-doped Barium-122 compound. Probably the most interesting thing about this phase diagram is that the material is a high temperature superconductor. And I think the second most interesting thing is the behavior of the electrical resistivity in the normal state. In particular, as you dope the system away from the antiferromagnetic phase boundary, there's a kind of qualitative change in the temperature-dependent resistivity. This is maybe more clearly seen in resistance versus temperature traces, where you can see a change from T linear dependence of resistivity to more T squared as we dope away from antiferromagnetism. And this suggests that somehow remnant antiferromagnetism or quantum criticality is really affecting the transport characteristics in this regime of optimal superconductivity. And this idea has existed for a while that the transport behavior of the normal state is actually somehow correlated to the strength of the superconducting state. Here I highlight a few modern papers on the topic, especially Ian Hayes's paper. Stay tuned for the next talk. where you can kind of see correlations between transport coefficients and the superconducting state itself. So this is why it's important to understand transport. The issue is that much of the data in this most interesting regime is only available above 30 Kelvin, above TC. And generically, you start to see phonons come in at those temperatures, and it becomes very hard to separate out, okay, what is an anomalous source of scattering and what is a more conventional source of scattering. So the low temperature data is extremely useful for a transport measurement. And this is where magnetoresistance comes in. One way to get data at low temperature is to just put the sample in a giant magnetic field, and you can get a resistive signal once you kill superconductivity. There's an added bonus, which using magnetoresistance, you can to some extent evaluate anisotropies in the scattering rate or Fermi surface. But most of these goals are kind of contingent on having at least a base level understanding of the mechanism for magnetoresistance. And that's proven fairly difficult. So there's been several experimental papers on this topic. I would say this kind of started in 2016 with Ian Hayes's paper on phosphorus doped barium-122. But since then, you know, many quantum critical systems have shown qualitatively similar behavior. And there's kind of three main things that we can take away from the existing data. One is that the magnetoresistance generally has this kind of hyperbolic shape, meaning it's B squared at very low fields, but then there's an extended range of linear and field resistivity. The second is that it seems to be kind of disproportionately sensitive to temperature. This was noticed by Ian Hayes originally, where you can just scale magnetic field by temperature and resistivity by temperature, and it seems to capture all of the low temperature data very accurately. And then probably the most beautiful aspect of this data is it seems to apply fairly generically to a bunch of different materials. So I've shown, you know, some examples here: chromium arsenide under pressure, iron selenide, the sulfur doped iron selenide, and then electron doped cuprate. So any type of mechanism that we propose needs to be, in some sense, easy to generalize, or not super dependent on specific electronic structure details. So I'm going to focus on barium-122 in my talk. Like I said in the previous slide, many of the magnetoresistance studies have focused on this kind of region of optimal superconductivity. And rightfully so. You know, this was the original motivation for magnetoresistance measurements. In my talk, I'm going to first focus on the spin density wave state, and then slowly move over to the quantum critical regime, and we can see how things evolve from the spin density wave state. So first, I'll describe our experiments on linear magnetoresistance in undoped barium-122. This is an antiferromagnetic metal. The resistance versus temperature follows fairly well a t squared plus t to the fifth dependence. Okay, this is something that you expect for scattering from antiferromagnetic spin waves. So we don't necessarily expect many anomalies in the scattering rate in barium-122, but at low temperature, we see a linear magnetoresistance over an extended field range. And this is reminiscent of what's observed in the quantum critical regime. So this kind of motivates us to look for a mechanism that's based on orbital motion rather than some type of anomalous scattering rate. Okay, so let me describe orbital magnetoresistance and then one simple change that you can make to this model to see H linear magnetoresistance over an extended field range. The typical way to understand magnetoresistance, at least in what's called the relaxation time approximation, is you apply an electric field to the Fermi surface. And then when you apply a magnetic field in a perpendicular direction, the Fermi velocity of the quasi-particles will be averaged over these orbits, cyclotron orbits. And for most Fermi surfaces, the magnetoresistance that you get looks something like this. Okay, it's B squared at low fields and saturates at high fields. And there's a very, very narrow range of H linear dependence, if it's there at all. It's really more of a crossover regime between these two different extremes. Okay, but we can make a simple change to this model. Here I'm showing simulations of the magnetoresistance of this Fermi surface. Let's say it's 2D. And what I'm going to do is increase the curvature. So you make these points more and more kind of cuspy, up until the point that it's completely a square. And if it's a square, then the magnetoresistance is linear down to zero field. This is a known mechanism. This has existed for a very, very long time. The idea is that when a quasi-particle is executing a Lorentz orbit, as soon as it hits this cusp, the Fermi velocity is rapidly shunted into a perpendicular direction. And so effectively, these regions act like quasi-particle sinks. And the fraction of the Fermi surface that gets affected by this quasi-particle sink is linear in field. It's just proportional to the Lorentz force. So it's actually fairly rare to observe a Fermi surface that looks like this. But we have good reason to believe that the Fermi surface of antiferromagnetic Barium-122 may have these sharp cusps. Here I'll show a cartoon. So you have a whole Fermi surface at the center of the Brouillon zone, electrons, Fermi surface at the corner, and they get nested, imperfectly nested by the antiferromagnetic ordering vector. And when a gap opens up, you get these banana-shaped pockets with these regions of large curvature at the corners. To some extent, this has been observed in ARPA's experiments on Barium-122. These are actually simulations of the Fermi surface, and experimental data can somewhat see these banana-shaped pockets. So our collaborator, Alex Koshylev, did a calculation of what the magnetoresistance of this, this type of shape in the Fermi surface of Barium-122 will look like. Okay, and there's a few magnetoresistance parameters here, and they depend in a somewhat detailed way on the fermiology and the scattering rate and things like that. What we did is we went to low temperature and used some reasonable values extracted from literature or our own experiments for the scattering rate, and we're able to model the magnetoresistance data fairly well. So blue is the experimental data, and red is the calculation using these parameters. This is, you know, there's a lot of uncertainty in these parameters, so this should not be taken as kind of quantitative proof that the model is correct, but it's more of just a sanity check of the model. And something interesting to note about this is that these magnetoresistance parameters depend on the antiferromagnetic gap. That sort of determines how cuspy the Fermi surface will be. And then because that strong turning point region primarily dominates the magnetoresistance, the relevant scattering rate is the scattering rate near that cuspy region, as opposed to the average scattering rate on the Fermi surface. So you can see this when you do temperature-dependent measurements and extract the scattering rate from the magnetoresistance as opposed to the overall resistivity. The scattering rate near these cusps, near these kind of nesting points on the Fermi surface, increases much more rapidly as a function of temperature. And this is kind of expected. So as you increase temperature, spin density waves will be excited, and they cause higher scattering at points that are nested by the antiferromagnetic order. Okay, next up phosphorus.
Sorry, yeah. Can I ask a question? How do you sort out the scattering rate from the magnetoresistance?
Yeah, so it's basically these parameters depend on scattering rate, and they depend on primarily the scattering rate in this vicinity of that turning point. So this model is the magnetoresistance only of this region. Which may not have the same scattering rate as the rest of the Fermi surface. Yeah.
But the gap is changing.
The gap may change. That's correct. Yeah, yeah. So that is not taken into account in this plot right here. Okay. Yeah, that's a good point. So let me move on to the phosphorus substituted. Right, you make a good point. So these plots are meant to be kind of qualitative illustrations, and at least at reasonably low temperature, we can believe that the magnetoresistance is primarily controlled by the scattering rate. And then as we phosphorus dope the system, okay, this kind of anisotropy becomes more and more pronounced. You know, in 19% phosphorus substituted Barium-122, we see a very similar type of linear behavior in the magnetoresistance at high fields. And one of the interesting things about this highly anisotropic scattering rate is because the magnetoresistance is primarily controlled by these two parameters, and we observe that the temperature dependence is much stronger than the zero temperature value. So effectively, both of these parameters go as T squared, like the scattering rate, plus a relatively small constant. This leads to a very simple scaling relation for the resistivity or the magnetoresistance, where you can divide the resistivity by temperature squared and the magnetic field by temperature squared. And we see that it fairly well captures the experimental data. Okay, and this is reminiscent of what happens in the quantum critical samples, where you see the scaling with magnetic field divided by temperature and resistivity divided by temperature. Although in this case, in this case, given the model that we've applied, it seems to be the case that this kind of hyperbolic dependence on field arises due to these quasi-particle sinks on the Fermi surface. And the scaling with temperature may be due to a highly anisotropic scattering rate. Okay. So, I've already hinted at this already, but as we move towards the quantum critical regime, this gap kind of closes. And also these points turn into regions of very strong antiferromagnetic scattering. This is called the hotspot model. And this is a very, a very well-known theoretical model. But it turns out that these regions of very high quasi-particle scattering can also act as quasi-particle sinks. This has been explored by Achim Roche and Alex Koshelev as well. Actually, Alex Koshelev did this calculation of magnetoresistance specifically for the Fermi surface of Barium-122. What he did is model the scattering rate near this hotspot as a Lorentzian, and the specific parameters of this Lorentzian are dependent on spin susceptibility, as well as the scattering cross-section with these antiferromagnetic fluctuations. And the magnetoresistance that you get from this looks almost identical to the magnetoresistance you get in the previous model. It's basically B squared at low fields and crosses over to linear at high fields. Now there's a few experimental tests we can do. So here I show what this magnetoresistance parameter is, what it looks like. There's this coefficient, which is a very complicated function of spin susceptibility parameters in fermiology. It's very difficult for us to calculate this and compare to experimental data because there's a lot of unknowns here. One of the things we can compare is the dependence of these parameters on the background scattering rate. So in this case, because these calculations are not done in the relaxation time approximation, the transport properties will depend on sources of scattering in somewhat of a nonlinear way. So if you increase the background scattering, that has this very unconventional square root scaling on the magnetoresistance parameters. And this is something that we can test. So what we did is took samples of optimally doped, the quantum critical Barium-122, and irradiated them with alpha particles at Lawrence Berkeley lab, okay? And you can see the effect on the zero field resistivity. The effect is to basically increase the resistivity in roughly a temperature independent way. Okay, and then several of these samples were taken to pulsed field and were able to do a detailed disorder and temperature dependent experiment on the quantum critical Barium-122. So shown in the black lines are the calculation curves, the modeling based on Alex Koshelev's model. And in all cases, we can do this simple scaling relation where we divide resistivity by temperature and magnetic field by temperature. And as you disorder the system, the magnetoresistance decreases overall, and the coefficients of the scaling function change slightly.
Nikola, do you mind if I interrupt just for 1 second?
Sure, yeah.
So you do this analysis for the magnetoresistance, but it seems like if I look at the temperature dependence, as you change the disorder, that will affect strongly the cold region contributions, right? So I'm somewhat surprised by this linear resistivity slope that seems to be, to a zero order, not too sensitive to the amount of disorder, which I would not have expected this cold spot, hot spot model to describe that.
Right. Yeah, so that is a good question. I think one answer could be that we're not in the right regime of temperature. Maybe you expect to see the strongest changes to the temperature-dependent resistivity below 30 Kelvin. Another answer is that the hot spot, cold spot model is not the correct description of the T-dependent resistivity. Mm-hmm. Right. Yeah, it's difficult to say whether the disorder will affect the temperature-dependent resistivity in this low-temperature regime. Yeah, so
for the magnetoresistance, when you go to very high field, mm-hmm. are you getting an H square, or is it still linear?
For magnetoresistance, when you go to a very high field, you see H linear behavior.
Always. This is very different from the cuprates, because in the cuprates we did find the H square in very high fields.
I mean, to some extent, it depends on what temperature you're measuring at. So if you're at high temperature, you do see a B squared variation. So
I am speaking of measuring cases which are near the optimum TC in the cuprates.
Yeah, I know there's been certain cuprates, I think LSCO, where there's a linear magnetoresistance near the optimal TC.
We also see it in very overdoped cuprates as well, the appearance of this linear magnetoresistance at high fields. But I think your point in IPCO is clear that it's mostly quadratic there, but it might be the field scale, as Nikola said.
This is very strange, a very big difference.
Yeah. You need to, I think it's important to consider what the Fermi surface and scattering rate look like. Also, if you have very clean samples, the cold spots of the Fermi surface can give a significant contribution.
In the cuprates, when we we did a lot of work dirtying the samples, and when you dirty them, they are still square, H square.
Okay, that's interesting. Yeah, it's might be interesting to compare. So where was I? Let's see. Yeah. So okay. So we've done these calculations. Alex Koshelev did these calculations for temperature dependent and disorder dependence of the magnetoresistance, and in particular, the predictions of the model are a T-linear variation of these magnetoresistance parameters. This just comes from the fact that antiferromagnetic scattering is T-linear specifically at the hot region. And then the square root dependence on disorder. And we see a T-linear variation in these parameters, and also to some extent you can fit the disorder dependence with the square root function. Now you only have 3 data points. It's not the most striking observation, but you can easily test using Kohler's rule whether the disorder scattering rate adds in a linear fashion with all the other sources of scattering. One of the assumptions of Kohler's rule is that scattering rates add linearly. And at 4 Kelvin, as we change the disorder level in our samples, there's a clear failure of Kohler's rule. So this strongly points to an anisotropic scattering mechanism. So just to summarize, Alex Koshelev's model and calculation for this material is able to capture several features of the experimental data: the hyperbolic shape of the magnetoresistance, the linear variation of the MR parameters, and also this unconventional disorder dependence that we've seen in our experiment. Yeah, so that's the kind of the end of my talk. I've presented linear magnetoresistance in underdoped and optimally doped barium-122. And then we have an orbital model for this behavior, which is based on these quasi-particle sinks. In underdoped barium-122, these are regions of large curvature, which slowly evolve into hotspots. Okay. I will just mention that, while these calculations have been done for barium-122, we might expect this mechanism to generalize to other materials. So for example, let's say the cuprates, you may have regions of the Fermi surface that have large curvature. This is a tight binding calculation for neodymium doped LSCO. Or you may have regions of the Fermi surface that have a very high scattering rate. And these can both act as quasi-particle sinks and in fact give rise to linear magnetoresistance. You know, this is from Brad Ramshaw and Louis Teifer's paper, recent paper on cuprate magnetoresistance. And they were able to observe just simply using a Shockley tube integral that the magnetoresistance in high fields can be linear if you have very anisotropic scattering. So that's the end of my talk. I hope I didn't go over time. Thank you for listening.
Great. Thank you, Nikola. Before I turn over this to the question answer period, I just want to announce that we will not have the seminars next week, but 2 weeks from now, we'll have Ian Gallas from University of Paris and Heike Fall from Stanford talking about nematicity and related issues. So with that, any questions, comments? Penchen, please.
Yeah, so I was, yeah, very nice talk, yeah, Nikola. Yeah, so I was very curious, does the MR effect in your case dependent on the current direction within the AB layer? I mean, which direction you're applying the current?
Yes, I have not studied in detail for underdoped samples whether it depends on A or B. In all cases, we're applying in the A direction.
Okay.
In optimally doped.
Yeah, it's tetragonal, right? Optimal dope doesn't matter. But
yeah.
Whether 45 degree makes any difference, because you're arguing that this MR effect is basically opening up the gap. You know, I mean that has a particular direction, right? In real space.
It does, but I think if you have tetragonal symmetry, it shouldn't.
No, but I mean, if you apply 45 degrees, you know, then yeah.
Between A and B.
Yeah.
Yeah, I'll have to think about it. Maybe that's something to try. Yeah.
So your field is along C axis, right?
Field is along C in all cases. Yeah.
Okay. Thank you.
Yeah, we have a question by Romer Hirompe. Please go ahead.
Yeah. Hello. Well, thank you for the talk. It's very interesting. On this slide, actually, if in the graph on the bottom right, if you would zoom in on low h/t, then you start to develop their deviations at low h/t, whereas in the sample without irradiation, you don't see such deviations. Do you have any explanation for that?
Yeah, I mean, I can tell you why this is happening. This is happening because the curvature of these curves is changing slightly. It's actually not perfectly T-linear. So especially in disordered samples, you start to see at high temperature, it kind of has this spoon shape. I can't explain to you, you know, why in particular you start to see deviations at high temperature in the context of this model. But it's a reflection of the fact that the temperature-dependent resistivity is changing slightly.
Okay. Thank you.
Yeah.
Nigel, please.
Yeah, beautiful work, Nikola. Thanks for your talk. So looking at this slide, clearly, you know, you have this sample with a residual resistivity well over 150 micron centimeters. I was wondering, it'd be very interesting to see, you know, how this evolves. I mean, do you have at least preliminary data on that, or is just the magnetoresistance too small to resolve this kind of scaling in that particular?
Yeah. Unfortunately, we don't have data because this was, you know, right about when we were putting this together is when the pandemic hit. So we were not able to measure these most disordered samples. That's something to do in the future. Yeah.
Does the disorder survive if you heat it up, or does it go away?
Yeah. So all of these are heated up to room temperature after irradiation, or during irradiation. They're actually.
Okay. Okay.
Yeah.
So it could survive. All right. We'll watch this.
Timur, can I? Yes, Timur, can I?
Go ahead, please.
Yes, this system, phosphor-doped Barium-122, certainly we know that it has multi-pocket, Fermi pockets. But your picture concerning which pocket, and it's because we have the hole and the electron pocket here.
Yeah, so both pockets are considered. It's basically a scattering between these pockets. That's the scattering.
Ah.
So orbital motion will occur on both pockets.
You mean the scattering between the hole and the electron pocket, or within the pocket?
This antiferromagnetic scattering occurs between pockets.
Oh, I see.
Yeah.
Okay,
that's right.
I see. So it's a is this scanning result has any relation to the superlinear resistivity? I mean the temperature dependence.
It's difficult to say. I mean, this is one of the kind of main questions, is whether you can recover the temperature dependent resistivity based on this hot spot and cold spot model. I don't think there's a good way to do that at present. So it's, in our work, we're not able to capture the temperature dependent resistivity.
I see.
Yeah.
Okay. Okay. Thanks. Yeah.
I would like to have a comment on that. Okay, because in this work of Achim Rosch, he showed that if you are at a quantum critical point and have a disordered system, then the hot spot, cold spot interaction will be stronger. And because when you go away from the quantum critical system, or if you put in more disorder, then the system evolves into a different type of universality class. So the resistance, for instance, changes as with the temperature from T to the 3/2 to more almost linear behavior. And I was wondering whether you see any of that in your work.
Yeah, so this is kind of similar to the question that Chimiao was asking about the fact that we don't seem to see very significant changes in the temperature dependent resistivity as we disorder the samples. So, you know, like you mentioned, Achim Rosch's paper, you should see kind of qualitative changes in the power law with disorder, but it may be a question of we're just at too high of a temperature. You know, we have to go through in detail through Rosch's paper and see, you know, what are the different temperature scales involved in these different scaling regimes. So it's not something that I have a good answer to.
Okay, well, thank you.
Mm-hmm. Yeah.
I still have one remark. Can I go on?
Yeah, go ahead, Farley.
This system being multi-band, in principle, the scatterings are not going to be the same for the various bands. So the analysis that is done, which is similar to that done in the cuprates, is done for a single band model, where you think that the band has the hot spots and the... So in any case, you also have other bands. So when you look at a resistivity or magnetoresistance, you are seeing things which are adding the conductivities of the various bands. And that makes it more difficult to analyze than the case of single band models like the cuprates. What do you think about that?
I mean, you're correct.
We have done very, very careful work on the cobalt 122 with Florence Rulli-Albin, in which we have tried to analyze the transport in terms of two bands and two different scattering rates, etc., showing that they were very similar. And in fact, in that case, we find a t-square term and not even a t-linear. Here, all this is done as if it is a single band.
Yeah. So, so in your work, were you looking primarily at the temperature-dependent resistivity?
Yeah.
Yeah. So the thing about the magnetoresistance is it's true that you will get contributions from you know, each band individually. Mm-hmm. The regions that dominate the magnetoresistance are actually these quasi-particle sinks. So in our work, we've actually completely neglected the magnetoresistance arising from these cold regions. Okay. You primarily consider this nesting point. So
you have to consider the band which has the nesting points and consider it primarily.
Yes. Yeah.
Okay.
Yes. Yeah. So there's not a one-to-one correlation between resistivity and magnetoresistance. Resistivity, you need to consider everything. Magnetoresistance is dominated by these very small regions.
Well, that's what you think.
That's what I think. Yeah.
But regardless, Henry, I think the magnetoresistance is really, really interesting, because if I just look at the temperature dependence of the resistivity, it looks very similar to all the other quantum critical like materials, heavy fermions, etc. And also, Chen actually has E over T scaling in this optimally phosphorus doped case that also looks quite similar to the other cases. So one could ask question, given these seeming universalities, does the magneto-resistance tell us some variations across these different materials? And that,
I agree. I am puzzled by the fact that you don't find H-square magnetoresistance at high fields. But okay, because this is the only thing you expect once you have eliminated all the quantum critical fluctuations, etc. Okay. This is hard.
If there's no more further questions, actually, thank you, Nikola, for staying within time, and it's a good model.
Thank you very much. Nice talk.
Thanks very much, a very nice talk. Let's move on to Ian. You ready to go, Ian?
Yes, I am. Let me share screen and hope this works. All right, can everyone see my screen?
Right. Okay, great. So next we have Ian Hayes from University of Maryland, continuing on the theme of quantum criticality. Please, Ian, go ahead.
All right, thank you very much, Janelle, and thank you very much for the opportunity to speak here and share what I think are some pretty interesting results on specifically the magnetic field dependence of the Hall effect in this phosphorus doped system. First, I'll just do a brief outline of the talk. I'll start with just a few words about what I mean by strange metal behavior.
Ian, I don't know whether it's me or whether others felt the same way. The voice didn't come across.
Yeah, maybe.
Can you hear me at all?
Yes, we can
I think
hear,
if you get closer to the microphone, it might be.
Yeah, there's echo.
There's echo. How about if I'm here?
Yeah, much better. Yeah.
That much better?
Yeah.
Okay, I'll hang out close to the camera.
Thank you. Yeah.
Okay. So yeah, the outline of my talk is I'll just start with a few words about strange metal behavior in high TCs, and then move on to this field dependence of the Hall effect in the phosphorus doped series. And to give you this sort of highlight, the field dependence is sort of going to give us a new way of characterizing where the strange metal behavior lives, and therefore what it's correlated with in the phase diagram. So in particular, it reveals a fairly clear critical fan in the temperature and doping phase space that suggests this behavior is linked to fluctuations of the ordered phase. And it's also going to show a very strong correlation with superconductivity, specifically in the zero temperature limit. So I'll show you those in due course. And then hopefully I'll have a few minutes to say what I think the broad implications are of this, of these results for strange metal physics and high TCs. And if you have further questions on this that I can't answer today, I'll just point you to the paper we just published on this exact subject just a few months ago. And of course, I need to start by thanking everyone who helped make this possible, including our previous speaker, Nikola, who helped a lot with these measurements, Professor James Annelides, and our fellow Berkeley student, Zayu Hao. And then, of course, the many people at the National High Magnetic Field Lab without whom we couldn't do these high field experiments, in particular, Ross McDonald, Arkady Schechter, Mun Chan, and Brad Ramshaw were very helpful in this. And this work's been supported by the Gordon and Betty Moore Foundation primarily. So to start with strange metal behavior in high TCs, people sometimes mean a lot of things by this. For my purposes, I'm just referring to the common set of transport properties that seem to characterize all these compounds, particularly near optimal doping. So the most famous example of this is the T-linear resistivity. And people will say this is strange for a variety of reasons. Either you can go to the low temperature limit, so it looks like you don't have quasi-particles, or maybe you cross the Matjaffa-Rega limit. For my purposes, I just care that the T-linear resistivity is this thing that is correlated with optimal TC in lots of cuprates and now lots of nicketides. So the T-linear resistivity is a famous piece of this, but there's also behavior in the Hall coefficient that is common to all these systems. So most cuprates show a strong temperature dependence, usually an enhancement, but sometimes it's a change in sign of the Hall coefficient that is strongest near optimal doping. And this isn't even limited to just high TC materials. Other unconventional or quantum critical superconductors show something like this. So cerium cobalt-indium-5, I have an example over here on the left, shows a strong change in RH that is strongly associated with just the sort of critical region and highest TC. So this does seem to be a consistent feature of the superconducting state, or so I should say, superconducting materials in a broad class of compounds. Now, I probably don't have to introduce phosphorus-doped barium-122 here, since we just heard a lot about it. But what I want to highlight here is that the observations we made previously about parallels between the field dependence and temperature dependence in the resistivity motivated us to look at the field dependence of the Hall coefficient and to ask whether there was some way in which the field dependence there gives us another way of characterizing the strange metal behavior, what it's correlated with and where it might be coming from. That's really the motivation for the data that I'm gonna show you now. So start with optimal doping. This is the Hall coefficient at low fields for optimally doped barium-122, 31% phosphorus substituted. And I should start by saying that for all the data I will show you, the field current configuration is that current is passed in the field, in particular along the A-axis, and field was applied along the C-axis. That'll be the same configuration for all this data. Now, looking at the temperature dependence here, there's temperature dependence all the way up to 300 Kelvin, but especially at low temperatures, you start to see a sharp upturn that is reminiscent of what I just showed you in the cuprates and in some heavy fermion compounds. And so the question we'd like to ask, is there any distinctive field dependence in that region? So if you go to the middle of that upturn, somewhere around 75 Kelvin, and measure RXY, the off-diagonal resistance as a function of field, you'll see that it's actually sublinear. So if you were to define an effective Hall coefficient at each field, that's RXY over H, say, then you would actually see it's decreasing with field, qualitatively similar to what happens when you increase temperature. And furthermore, this only happens within this low temperature upturn region. So if you go up to 200 Kelvin, you get a very straight RXY all the way up to 60 Kelvin. So this has the makings of an interesting correlation between a particular field dependence, a decreasing RH with field, and the strange metal property or the strange metal behavior in the temperature dependence, increase as you go to lower temperatures. And I will show you, based on where this particular field dependence lives in the phase diagram, that it's very unlikely to be a simple band structure effect. Probably is related to whatever scattering, whatever interactions are responsible for superconductivity. But as was mentioned many times in the previous discussion, barium-122 is a multi-band system, and so you can get both temperature changes in RH with temperature and changes in RH with field in very simple multi-band physics. So I just want to say a few words now about what one expects for a system like barium-122 based on the simplest multi-band model. So if you have multiple bands, the sort of simplest thing to do is add the conductivities in parallel, and it's a Ashcroft-Merman level problem to just put them together. And there are just two limits I'd like to highlight for you. One is the H equals 0 limit. In the H equals 0 limit, you get a Hall coefficient It's just the weighted average of the Hall coefficients on the different surfaces, weighted by the conductivities and their respective surfaces. And then there's the high field limit, in which you get an effective RH that is determined by the total carrier number, electrons minus holes. And so generically, in a system like Barium-122 that has electrons and holes in approximately equal numbers, you'll start from a fairly small RH, because these two terms will nearly cancel. You'll go to a very large RH as your N total, electrons minus holes, goes towards 0. So the generic thing you'd expect for this system is for RH to start out small and get large. If you were to have two carriers of the same type, then you'd expect the opposite behavior. It starts out high and then gets smaller. And because Barium-122 has 4 bands, this is a possibility, but there's quite a bit known about the band structure of Barium-122. And in particular, in the phosphorus subseries, there's actually quantum oscillations that give us some idea about what the relative mobilities are on those two electron-like sheets, which dominate the Hall coefficient. And they are close to equal. They're within 50% or maybe 100%. And so that allows us to do just basic simulations and ask how much field dependence should we expect from that? And the answer is not very much. You still expect the hole and electron balance to dominate and for the Hall coefficient to simply increase with field. You would need a sort of unrealistically large difference between the mobilities on the two electron sheets to get a low field decay in the Hall coefficient. And even then, it's not going to be very large. So this can't rule out multiband effects as the origin. There's a lot of effects one could layer on top of each other to get very complicated behaviors in the Hall coefficient. But it's at least not the natural thing in the first order calculation that you would do. And as I'll show you, what I'm calling the strange metal field dependence, where RH decreases with field, is confined only to very special parts of the phase diagram. All right, so back to data. I just want to show you more generically what RH looks like. So in the rest of the talk, I'll just plot RH, which I'm defining here to be R rho xy over the field, because that's what gives you it's what makes it easiest to see the field dependence. And so generically, what you see throughout the phase diagram is some region of decreasing RH, which flattens out, the field dependence decays, and eventually you get an upturn, an increase in RH at high enough field. Since that's what we expect from multiband physics, that's naively what we'll attribute it to. And in fact, you'll see eventually when you get to the far overdose side of the phase diagram, pure H squared is in fact what you see. Other than that H squared, the curve is sort of generic. And so what I'm going to show you next is basically how much you can decrease RH by applying a large field throughout the phase diagram. If you want more details on how we do this, I'll point you just to the paper we published, or we can talk about it later. I don't want to spend too much time on it because all of the important correlations that I want to talk about are readily seen in the raw data. But just to focus on, just to give you a basis for what I'm going to show you in the next slide, throughout the phase diagram, we try to estimate how much can you actually decrease RH by applying a large field. So when you do that, this is what you get. This is an intensity plot for that strange metal field dependence in the doping and temperature plane. And I've started here at 30%. I've neglected the underdoped part because the transition to the antiferromagnetic phase involves reconstruction, as we heard in the last talk. And that radically changes the Hall coefficient and gives you different field dependence. So to compare apples to apples, we're going to stay on the disordered side. And there are two things I really want to draw your attention to about this phase diagram. The first is that if you look at high temperatures, the strange metal part of the Hall effect is independent of doping. Throughout the very broad region of doping space, you simply get the same field dependence for all your samples. As you decrease the temperature, the window over which that is true decreases. And it decreases continuously and seems to vanish near 30%. And thereby traces out the kind of fan region that you would often draw when describing quantum critical systems with a single tuning parameter. So this looks very much like there's some detuning energy in the system that is getting stronger as we move towards higher phosphorus doping, such that if temperature is larger than that detuning energy, you simply get the same effect, independent of what your actual doping value is. So this is striking. There aren't too many things in too many experimental observations that actually paint the fan in quite this clearly. So this is fairly striking evidence in favor of the idea that this effect is coming from the influence of the nearby ordered phase. The second thing I want to draw your attention to is what happens at low temperatures. So when you cross that fan-like region, the strange metal field dependence weakens, and it continues to weaken, but it doesn't weaken all the way to zero at zero temperature. There's an extended range over which you still see a decreasing RH with increasing field, and it's strongest near optimal doping, and it decreases for higher phosphorus content, and then vanishes at the same point that superconductivity vanishes. So if you go just beyond the superconducting dome at low temperatures, you see none of this decreasing RH with field, you see pure H squared. You can recover the decreasing RH with field if you go to higher temperature, but specifically the low temperature part of the Hall coefficient seems to be strongly correlated with superconductivity.
Ian, do you mind if I interrupt you?
Yeah, not at all.
If I take the dashed line literally, it's somehow in deviation with my understanding of what happens in the phosphorus doped materials. In other words, the scale doesn't, the critical slowing down doesn't actually go all the way to zero, that even at around optimal doping, there seems to be various indications that there's some truncation. So the dashed line, in that sense, I would have thought that, you know, it doesn't really terminate to zero.
That could well be true. So it's a little difficult for me to answer with the high fields data because of the very limited field range available at optimal doping. So I'll show you the raw data in just a little bit. When I do the fits and try to estimate how large the strange metal RH actually is, it does top out at around 10 to 15 Kelvin or something. Okay. So that is potentially consistent with that. If you have some cutoff of about a few Kelvin in this sample. The other thing I'll point out is that the antiferromagnetic phase actually ends at 28%. So I'm a bit off the exact critical points, you might say. And that was chosen to just make sure we avoid any accidentally entering the antiferromagnetic phase.
Fair enough.
Your observation is fair, and this is really just a guide to the eye determined by the data points that I have. And there's only so much I can say down here. But it may well be consistent with a small cutoff. So let me start by showing you what the data looks like at low temperatures. So these are just slightly overdoped samples, 36 and 45% phosphorus doping, so they live around here. You can see a strong decrease in RH at moderate temperatures of 25 Kelvin or so. And then that decrease definitely weakens as you go to lower temperatures. At higher fields, you can see that the increasing RH is setting in again. And in between there, there's sort of a balance between the two. So you can see it's a little bit stronger for the 36%, whereas at 50 Kelvin, you're already moving into the H squared regime for the 45% doped. In each case, there is still a bit of decrease that you can observe. And if you continue all the way to the overdoped, the very edge of the superconducting dome, at like 73% phosphorus substitution, this is a sample with an about 1 Kelvin TC, it's right on the edge. You see a very small, 2% or so decrease in RH at a few Kelvin. And then if you go to the next sample over, you don't see any decrease at all at 2 Kelvin. What you see is a pure H squared fit, which seems, well described by simple multivariate. So you can see directly by eye that whatever this decreasing RH is at low temperatures, it vanishes at the same time as superconducting. Now, the second thing I'd like to show you in detail in the data is what the fan looks like at higher temperatures. So if you go to very high temperatures, what I've plotted here is RH minus RH of 0. So this is just the field-dependent part of RH, which I do to compare samples from different parts of the phase diagram that have fairly different background RHs. Now I just want to bracket this for a second and point out that this is what you expect to happen just from multiband physics. The conductivities on all these sheets are getting better as you go toward the overdoped side, and so you expect this term to get smaller and smaller as this in fact does. But if you just compare the field-dependent part and just look at this decrease of RH with field, that part is exactly the same at high temperature. It's fairly small, but it's resolvable, and the curves lie right on top of each other. If you go to lower temperatures, there's still a region in which curves lie on top of each other, but the most overdoped samples start to show a weaker field dependence. And if you go to lower temperatures still, that trend continues, with the intermediate dopings showing a slightly weaker field dependence, and the common field dependence existing only over doping near optimum. So once you just plot the field-dependent part of the Hall coefficient, it becomes relatively easy to see that there is a constant thing whose constancy is shrinking as you decrease temperature. And you can see this in the temperature dependence of the Hall effect as well, but it's a little trickier because of the background. This is one thing I really want to highlight about this use of the field dependence to characterize the strange metal behavior, is that it allows you to make sort of cleaner determinations about which part of the Hall coefficient is actually correlated with superconductivity and with proximity to the antiferromagnetic phase. If you look at the temperature dependent part, there's some slight temperature dependence at high temperatures. You see the upturn, this is the data you saw before, that can be suppressed with a large magnetic field. And if you go to the overdoped side, you still see the upturn, but it ceases growing at sort of successively higher temperatures, so that by the time you're on the overdoped side, it still looks relatively flat. And it would be fairly hard to characterize this background well enough to measure this without the field. So just to quickly recap those observations, by looking at the field dependence of RH, we're able to tease out a certain part of the Hall coefficient that seems to be correlated both with superconductivity and with proximity to the antiferromagnetic phase. It allows us to trace out actually a nice quantum critical fan. Now, in the time that I have left, I want to say just a few words about how this relates to other materials and what it might suggest about the broader picture of strange metal behavior in high TC. So first, I want to acknowledge that there's some recent nice work actually coming from Nigel's group on the field dependence of RH in thallium cuprates. And there are some qualitative consistencies here where the Hall coefficient decreases with field, and that weakens as you go to lower temperatures on the overdoped side. I'll leave it to you to read that paper and determine how similar you think they are. But I think it's a very interesting point of comparison and suggests that something about this may be universal to all these high TC materials. The second comment I want to make is that it's rather striking that this strange metal field dependence seems to come in as an additive term. In other words, the absolute value of the change in RH is the same as a function of field at high temperature across a range of doping, despite the fact that the zero field RH is changing quite a bit. And so if we think that this effect is coming from some change in mobilities or carrier densities, even something generated by an unusual anisotropic scattering rate or antiferromagnetic fluctuation, you still think that the effect would then be filtered through this multiband formula and the competition between the Hall coefficients on these 4 different Fermi surface sheets, which are all changing across the phase diagram. The fact that it gives just one field dependence makes it look a lot like it's coming in some more direct way, which is an interesting issue that's going to have to be explored further. And naively, it seems fairly difficult to figure out how to get that behavior. Then the next thing I want to point out is that this sort of extended range of critical behavior at low temperatures actually draws barium-122 into closer parallel with a number of cuprates which show some sort of extended critical behavior on the overdoped side. So there are a number of materials that show T-linear resistivity at low temperatures. LSCO has been shown to do so through high field measurements. Electron-doped cuprates, where you can measure the low temperature resistance fairly directly, also show a T-linear behavior that vanishes near the overdoped side. And those same films also show a logarithmic upturn at low temperatures that diminishes, that's often characteristic of quantum critical systems, that diminishes and vanishes at the same point where superconductivity does at the overdoped side. And this is nicely laid out in a paper by Nigel that contrasts the way criticality seems to emerge in pnictides and cuprates, whereas in the cuprates, you seem to have an extended region of some sort of critical behavior going up to the edge of the superconducting dome. The pnictides up until now have seemed more conventional critical systems in the sense that things are concentrated really near a point where the antiparamagnetic order ends. I think one takeaway of this observation is that there is more of a connection between these two scenarios than probably originally may have seemed. May have originally seemed to be. So you can see pretty clearly there's some region where it looks like temperature is exceeding some detuning energy and you're getting uniform behavior. And you can cross below that, but that doesn't result in a continuous decrease of the effect down to zero at zero temperature. The effect sustains itself for all superconducting samples. And so it almost makes it seem like in the pnictides, you can see two energy scales. You can see the main detuning energy, which gives you this fan-like region and some region of doping independence in the Hall response. Then there's some other energy or time scale that makes those fluctuations or the effect of those fluctuations in the transport non-zero all the way down to zero temperature. There's something that sustains the effect throughout this region. So that'll be an important avenue to consider in the future. The final thing I'd like to say about these results is that they provide potentially more information about the structure of the interaction that is responsible for superconductivity. So there's been a lot of work correlating the T-linear term in the resistivity with TC, and that's been seen in a lot of materials, cuprates as well as pnictides. And the analogy being that the stronger the scattering is, the stronger the interaction is, and therefore the stronger the attractive part of the interaction will be. The resistivity by itself doesn't allow you to factor out which part of the interaction, it doesn't give you any information about what part of the interaction is going to be attractive ultimately at low temperatures. Whereas in the Hall coefficient here, we see a temperature evolution of the behavior. We see some zero temperature part where the correction of the Hall coefficient seems to be exactly related to whatever attractive part of the interaction there is. And then you see some thermal evolution such that even non-superconducting samples can exhibit this behavior on the overdose side. So there's quite likely even more information present in the temperature dependent of the Hall coefficient here, once you've been able to factor out everything with the field. All right, so with those admittedly very broad statements about what I think the implications of these results are, I just want to remind you of the highlights. By looking at the field dependence of RH, you can isolate a fraction of the Hall coefficient that seems to correlate both with superconductivity and to exhibit this intriguing fan-like feature that seems to tie it to the behavior of the antiparamagnetic phase. And if you have further questions, I direct you to the paper we just published, or you can ask them right now. So thank you very much for your attention.
Thank you very much, Ian. Nice talk. Any questions, comments? Let's start off from Nigel.
Yeah, thanks, Ian. A very clear presentation. It's beautiful data again. And I guess I wanted to link back to Nikola's talk, where it shows, very striking agreements between the phenomenological magnetoresistance, the measurements and the theory of Koshylev based on Spot's picture, also around 31%. And so I was wondering, what are the specific predictions for the Hall resistivity within that model, and whether they show any relation to the data that you present?
So I think qualitatively can produce an enhancement of the Hall coefficient with anisotropic scattering generically. It has this sort of similar effect to having two sheets.
Yeah, but specifically the field dependence. Yeah.
Oh, specifically the field dependence. I think generically you do expect whatever increase in RH you get from anisotropic scattering to decrease with field. So that way it is actually consistent. What I would like to see, and haven't seen because I'm sure it's difficult in a system like this, is whether you can actually reproduce a consistent field dependence at high temperatures despite all these changing background conditions. It's probably not impossible. The question is whether you're just going to be tuning parameters at the end to make it fit.
Yeah, but it seems very, your data suggesting a very systematic behavior, which sort of almost independent model, which is kind of, of course, we've been measuring magnetoresistance and Hall effect, and we really struggle to fit the two side by side in any kind of Boltzmann type picture. I guess I think what you're saying is it's probably the same here too.
Yeah, I think, next to each other is fairly hard. So it may well be that a lot of the magnetoresistance is coming from details of the Fermi surface. And then there's some extra ingredient that shows up in the Hall coefficient that is just separate from the Fermi surface. It sits on top of it.
Very interesting.
It's unclear how they're related.
Thank you.
Any other questions, comments? Maybe I can ask sort of a question following the lead you were giving towards the end of your talk, connecting different materials. So the Hall coefficient in like heavy fermion quantum criticality going to vanadium doped chromium, etc. They seem to have very contrasting behavior, and there are various ways of analyzing it. But one way that has been fruitful in those two type of systems for comparison is to look for the isothermal dependence of the Hall coefficient and see whether, first of all, there's any rapid change in the vicinity of the quantum critical point, and if so, whether there's a sharpening as a function of temperature. And so in chromium systems, that the answer is no, there's not a huge change. And in any case, there's not a lot of sharpening. And in some of the heavy fermion quantum critical systems, the answer is yes, there's a very sharp change, and there's a very strong, very sharp crossover features, and that crossover feature sharpens as the temperature is lowered. And so you have this extensive, impressive collection of data in this system. And I was wondering whether something along that line could be looked at.
Yeah, so a question of how quick the transition is between, say, the totally normal Hall coefficient on the overdoped side and the optimally doped or underdoped behavior?
Yeah, because you say, you refer to the strange metal component of the Hall, and one could perhaps look at that.
Yeah, it's a good question. Looking at it in detail will be a little tricky because of the limits of high field measurement. Broadly, as a function of temperature, it sharpens a bit. So just looking at the color plot here, you can tell that there's a broader region of enhancement at intermediate temperatures, and it kind of sharpens up as you go towards lower temperatures. Can you describe what accounts for that difference between vanadium doped chromium and the heavy fermion material?
Yeah, it's tied up with the very drastic Fermi surface change on the two sides of the quantum critical point that happens in a heavy fermion system that doesn't happen in a more sort of conventional spin density wave quantum critical point.
Yeah. Yeah, to me, what's most striking here is that it doesn't seem to sharpen up totally, that no matter how low you go in temperature, there's some finite width here, which seems to characterize the superconducting dome.
Which might be related to the truncation of the quantum criticality on the temperature axis.
Okay. Is there something quantitative to look for in terms of the width of that behavior and maybe the truncation along?
In terbium rhodium to silicon to its linear in temperature for 1.5 decades of temperature.
Ooh. Okay, well that is a good suggestion.
Yeah, thank you. This is certainly a large body of data that you collected and looks really interesting. Any other questions, comments? If not, let's thank both Ian and Nikola for a really good combination for this fascinating story, evolving story. Thank you.
Thank you very much.
Very nice talk. Thank you.
Thank you.
Thank you. Bye.
Bye.
Bye, Jimmy. Bye, everyone.
Good to see you, Hilbert.
Okay, bye-bye.
Yeah, bye. Let's see.